Welcome to the Explainer, everyone. Okay, let's just dive right into this fascinating new paper from the Kimi team that completely rethinks how AI models remember information. If you've been tracking the explosive growth of large language models, you know that memory is the silent killer of performance. Today, we're looking at a breakthrough called Kimi Linear, which promises to fundamentally clear that memory bottleneck. Take a look at this friendly, open-source greeting from the Kami team. But hey, don't let the waving emoji fool you. This is setting the stage for some incredibly heavy, game-changing tech. What they're proposing here isn't just some minor tweak, it's a structural overhaul that they've openly released to the community, proving its worth at a massive 48 billion parameter scale. Like a good syllabus written on the corner of our whiteboard, here's our roadmap for decoding this complex, hybrid architecture today. We'll quickly cover the AI memory bottleneck, the attention compromise, Kimi Delta Attention, their 3-to-1 hybrid architecture, and finally, how it smashes the benchmarks. All right, starting right off with the AI memory bottleneck, or what I like to call the traffic jam of AI memory. So here's the deal. As we demand more and more from AI, like analyzing entire huge code bases, reading massive financial reports, or processing super long conversations, the memory traffic jam becomes literally catastrophic. Standard self-attention, which is the engine behind most LLMs, has to look back at every single word it's ever generated just to predict the next one. When you hit, say, 1 million tokens, that look-back process essentially grinds your hardware to a complete halt. And you can see the exact bottlenecks mapped out right here. First, we've got reinforcement learning test time scaling. Think of AI agents needing to simulate thousands of steps before they answer. Second, traditional Softmax attention has quadratic time complexity. That means as the sequence gets longer, the compute time squares. It blows up. And third, the key value cache, basically the model's short-term memory, grows linearly with every single token. It just physically eats up all your available GPU memory until the system runs out of space. Which leads us perfectly into the attention compromise, a tale of two competing models. If we were drawing a classic T-chart on the board, we're looking at a huge engineering trade-off. On the left, we've got Softmax full attention. It is super expressive and incredibly smart, but terribly slow and demands a huge memory footprint. Now, competing against it on the right, we have linear attention. This operates in linear time and uses a fixed, finite state memory, so it's lightning fast and memory efficient. But historically, it's unfortunately quite forgetful and really struggles with complex reasoning. To quote the researchers directly here, purely linear models hit a theoretical wall when trying to precisely copy or retrieve specific details from massive documents. Imagine asking a purely linear model to recall a specific serial number buried on page 400 of a manual. Because its memory size is fixed, it's probably already compressed or completely overwritten that exact detail. It just lacks the capacity to remember everything perfectly. This brings us to the real core innovation of the paper. Let's get into Kimi Delta Attention and fine-grained forgetting. What's really fascinating here is how KDA Attention, or KDA, entirely upgrades this concept of finite memory. Older linear models basically used a blunt forget gate, like erasing a whole chunk of your memory all at once. KDA introduces a channel-wise gating mechanism, which is just a fancy way of saying it acts like a highly selective filter, managing memory at a much more granular, dimensional level. Think of that finite memory state like this very chalkboard. Traditional linear attention uses a huge, clumsy eraser that wipes the whole board clean every few minutes. But KDA, it's a smart eraser. It assigns an independent forgetting rate to every single feature dimension. It literally gets to decide which specific, irrelevant lines of notes to wipe away to make room, while keeping crucial details, like that serial number we were just talking about, locked safely on the board. On top of that, they employ something called NOPE, which cleverly stands for No Position Encoding. Usually, models need explicit coordinates injected into their data just to know the order of words. But the Kimi team found that by stripping out explicit positional encoding from their global attention layers, they could delegate the complex task of understanding token positions and recency bias entirely to KDA. The smart KDM mechanism inherently learns sequence order through its decay rates. It basically acts as the primary position-aware operator, all on its own. Okay, let's look at how they actually build this thing in the 3x hybrid architecture. Structurally, let's stack these building blocks together. The researchers didn't just throw away full attention entirely. Instead, they built a hybrid. They stacked 3 fast, memory-efficient KDA layers in a row. These are your workhorses, processing information linearly and super quickly. Then they cap those off with one smart global full attention layer, specifically a multi-head latent attention or MLA layer. And then they just repeat that 3-to-1 pattern over and over throughout the network. The real genius here is that this exact 3-to-1 ratio marries the absolute best traits of both architectures. Some previous models tried mixing linear and full attention inside the exact same layer, which honestly just led to software nightmares and training instability. By alternating entire layers uniformly, 3 linear, then 1 global, they achieved amazing infrastructure simplicity. It's stable to train, super easy to parallelize on GPUs, and it keeps that vital global information flowing while shrinking the memory footprint. Now, whiteboard theories are great and all, but let's look at the hard numbers and see how it smashes the benchmarks. Just look at this number, 75%. By relying on those 3 linear layers for the heavy lifting, Kimi Linear cuts the key value cache memory footprint by up to 75% during long sequence generation. That means you can run much larger batches on the exact same hardware, or fit dramatically longer context windows onto a single GPU without crashing the whole system. That is absolutely massive. And this chart brilliantly illustrates the real-world speed advantage. Take a look at the right side. When you push that context window out to 1 million tokens, Kimi Linear isn't just slightly faster, because it isn't choking on a massive memory cache. It delivers a staggering 6.3x decoding speedup over standard full attention. It's generating tokens more than 6 times faster when reading something the size of a novel. So the obvious question, did they sacrifice accuracy for all that speed? The answer is a resounding no. Mapping these benchmark scores out, Kimi Linear actually outperforms the full attention baseline on massive long context retrieval tasks, which is exactly what linear models usually fail at. It scores 84.3 on Ruler compared to the baseline's 81.3, and it jumps up to 68.5 on Repo QA code retrieval, beating the baseline by over 5 points. That smart eraser really does work. And it gets even better when you look at the absolute bleeding edge of AI right now, reinforcement learning test time scaling. In really grueling, reasoning-heavy mathematical training, the accuracy of Kimi Linear grows faster and actually hits higher peaks than traditional full attention models. It solves much harder math problems on Math 500 and Amy 2025 way faster, totally proving this efficient architecture is perfectly suited for the next generation of thinking agents. Which brings us to the final thought I want to leave you with today. With the traffic jam of AI memory finally cleared by this elegant whiteboard theory made reality, we have to ask ourselves, just how far can we push the next generation of reasoning agents? If memory and speed are no longer our primary roadblocks, the potential for what these models can build, analyze, and discover just got exponentially larger. That's all for this explainer. Keep learning, and I'll catch you next time.